So our next speaker is Marco Cuturi, who will talk about the. So is it changed on the?
Maybe
on the zero ways to regularize optimal transport.
Yes. So I was starting with the title, which was Optimal Transport in Data Sciences. It's a bit different. So thank you very much to the organizer for the invitation. So my name is Marco Cuturi. I work at Google AI Brain in Paris and at Ecole Nationale Ecole Nationale de la Statistique et de l'Administration Economique, ENSAE, in the south of Paris. So this is joint work with several authors. I think maybe many of you here are familiar with Gabriel, whom I know is a regular visitor here at Cambridge. And then there's Ojun V, Francis Bach, Lénaïque Chiza, François-Pierre Paty, a student of mine, Hicham Janati, also a student, and Alexandre Grandefort. And let me just wrap up this slide by saying that we have a lot of the results I will be presenting here, or some of them, are contained in a recent survey that we wrote with Gabriel on computational aspects of optimal transport. So I assume that people in the room know a bit about optimal transport, and maybe some may not. So let me just go directly into some introduction. And well, the theory can be dated back to Monge. So Monge, a famous French mathematician, who's, I think, as you can show by his dates, survived the French Revolution, which is quite a feature for a French scientist at that time, and which is also very famous in Paris if you've ever happened to visit the 5th arrondissement around the École Normale Supérieure. There's Place Monge, there's many things, and Place Monge is one of the things to do, it seems, in Paris. So Monge proposed the main elements of this theory about a bit more than 200 years ago, 240 years ago now. And what the insight of Monge was motivated by applications, actually, by a practical public work problem, which was the following. Sometimes one has to displace Earth or any material given in some configuration, typically a probability distribution, towards another configuration which is more desirable. You want it to be in a different place. And this is the topic of this memoir. And so let me just try to give a cartoon perspective on this. Imagine you have a pile of Earth, which is standing there, and it has some volume or some mass. And we want to fill up a hole of the same volume with that sand. Okay? So if you ask anyone in the room probably how to do this in the 21st century, that doesn't sound like a very complicated problem. You would just simply push up all the mass with whatever machine you have, and then you're done, basically. But if you think about what happens in 1781, when there's not that many not much else but manpower, you have to take a shovel and bring the sand of each point of this pile of sand here, of this pile of Earth, towards the hole that you need to fill up. So mathematically, you can picture a worker equipped with a shovel going at each point x, and then picking up an amount of sand, which is basically the density of the measure at that point, mu of x. And this infinitesimal amount of mass is carried towards some point y, which we define to be a function of x. That's going to be the function of interest, and bring that sand from that point to that point. And in the course of doing so, well, we see obviously that the worker had to come across some distance, walk some distance, here d of x between x and t of x. And an important aspect of this modelization is to say that the work is proportional to this amount times the distance that you have to walk. Okay, so that's some other versions of optimal transport try to consider more complicated notions of cost, but this is the one that we will agree upon in this presentation. So it's the product of the mass times the distance. Now the problem of Monge is to find a map T that is optimal, for which the total amount of work that you will require from the worker is minimal. So the thing is, of course, you need to come up with maps T that have some meaning, in the sense that they bring exactly the mass here that is in the red pile of sand towards the blue and fill up exactly the hole, and don't put some sand around here or there. And so this you can encode easily mathematically by saying that for every segment B that you consider on the real line, if you define a map T, then there must be, well, at least you hope there will be, some x's such that t of x falls into B, right? And so if you write t minus 1b as a set, this is the inverse, the set of all the points whose image lies in B, then what you have as a very natural requirement is that if you, for instance, we assume that those are the segments that were landing in B, that the mass that is here is exactly equal to the mass that is needed there, right? So this is a push-forward constraint, and this must be the case for every possible B, of course, that you would consider in the real line. And so this push-forward constraint tells you that the mass of the inverse image of B under T must be equal to nu of the mass that you need at P. So to summarize, Monge considers the problem that among all of those maps T such that they push forward mu to nu, what is the one that minimizes the cost? And the total cost here is taken as integrating against all of the x's where there is a red mass, the distance between x and t of x. So there was not so much progress on this problem for about 2 centuries. But in the meantime, 150 years later, we had a different version of the problem that appeared. So let me try to introduce it here. So here is the Monge problem again, in a more abstract setting, of course, than just the real line or the plane. So we have a measurable space, we have a cost, which usually has nice properties, lower semi-continuous and things like that. But let me just consider a very generic setting. Mu nu, 2 probability measures in P, the set of probability measures in omega. And then the Monge problem is to find a map T such that T pushes forward mu to nu, and we want to minimize this. So as I was saying, there was not much progress on this problem for about 200 years because until Brognier in 1987, so 2 centuries later, found the following result, which is a landmark result in the theory of optimal transport, which is that if omega, so the set that you're talking about is Rd, and the cost is squared Euclidean distance, then if, to make simpler assumptions, mu and u are absolutely continuous, then there exists necessarily an optimal transport, and it has to be the gradient of a convex function. So whenever you find a convex function u whose gradient pushes forward this measure to this measure, then you know that you're optimal. You have found the optimal Monge map. So this is a very beautiful result, and it is actually playing increasingly a role in data sciences. But the problem with this formulation is that, and the problem in general with the Monge formulation, is that it must assume somewhat that the measure you're playing with have a nice regularity. They basically put mass, do not put mass on small sets, and you can very easily see why you might encounter problems. Imagine that I give you a pile of sand which is infinitely concentrated on the point, a Dirac, and I ask you to transport it to recover another measure which is kind of vaguely distributed. Then there's no way, of course, that the Monge map will map this thing to this thing. And the reason is that whenever I will apply a Monge map to this infinitely concentrated pile of sand here, I can only recover another infinitely concentrated pile of sand. So a Dirac maps to a Dirac. So that's the first problem. And the other thing is that this set of maps which push forward the first measure into another is not a convex set. So there are lots of computational issues that arise from that. So here comes the advance that I was mentioning earlier, 150 years later, which is that by Kantorovich, which we attributed to Kantorovich and other researchers like Tolstoy in the 30s and Hitchcock in the 40s. So all of them, of course, all of this appears more or less around World War II, where it really matters to be optimal when we move things around. And so the idea of Kantorovich is to relax this. So what is the relaxation that is proposed by Kantorovich? It's a very natural one. It's just to say that, so Monge focuses on the problem where a worker picks up a sand and drops it entirely at another point. What Kantorovich proposes is to relax this and say that the worker might pick up some sand, but basically distributed all the way in other areas. So instead of having a deterministic map that tells you that all the mass from point X goes to T of X, we will have a conditional map, if you want, that says that all the mass that is at X will be distributed according to a conditional distribution, which we could see as P of Y given that I have taken the mass, the sand at X equals X. So you kind of spread around the sand that you pick at one particular location. So if you actually write the problem in those terms, what you find is that the natural parameterization for this is to look at couplings. That is, probability measures, joint distributions. So if you were considering a space omega, now you are considering a space omega cross omega. And you're going to consider all of the joint couplings between mu and nu, meaning all of the joint distributions that have as the first marginal mu and the second marginal nu. And let me just illustrate what this means for instance, in this very simple case where omega is the real line. Here we have a distribution, univariate distribution mu, a univariate distribution nu. A coupling, in this case, will just be a bivariate distribution, which, when you push the mass in this direction, recovers mu, and in this direction, recovers nu. And the important thing about couplings compared to push-forward maps is that there is always a coupling that exists between any two probability distributions. And that's just the product of those marginals, like the independent coupling. And in this case, here I illustrate one coupling. There's another coupling. So these two things, for instance, are mixtures of Gaussians. And this thing here is just their product, just this independent coupling, mu of x times mu of y. This is something a bit more elaborated. So the Kantorovich problem, or the primal Kantorovich problem, as opposed to the Morse problem, is now something that's infinitely better behaved. Because this was a problem that was acting on a subset of functions from omega to omega, which had to satisfy this non-convex constraint. And this set may not even exist in some cases, if mu was not regular enough. Now, the Kantorovich problem is a problem where we have shifted the variable. Now we are optimizing over couplings. And this is a linear problem in the coupling. And this set is always non-empty. Now, the reason why we associate a lot optimal transport to Kantorovich is not only because he examined the problem, but it's also because he formulated the dual formulation of this problem. And historically, because this is one of the very first linear programs that was ever studied, and even was considered computationally, this was one of the very first dual problems that was considered in optimization theory. So the primal problem goes like optimizing over couplings, a cost which is linear. And here, the constraints in couplings are basically of the order of the size of omega and the size of omega, the two sizes of omega, if you want. Now, if you look at the dual, well, the dimension of the variable becomes the dimension of the constraints. So you have omega times omega constraints. And the variables now in the dual are of the size of the constraints in the primal. So we have omega plus omega constraints. So we are now integrating, testing two functions phi and psi against mu and nu under the constraint that phi of x plus psi of y is smaller than x of the cost c of xy. So this is in summary, this is the optimal transport problem. And the reason why this has been very popular in recent years is that, okay, we have here more or less defined an optimal transport problem. If the cost is a distance between points, then we recover something called the Wasserstein distance between probability distributions. And at this point, what this basically helps you is to find out whether two distributions are far from each other. What people discovered recently, about 20 to 30 years ago, is that whenever you define a distance, you may define an interesting notion of interpolation or interesting geometry on the things that you are defining the distance on. And here is a nice example. Here, for instance, I'm considering the set of all probability distributions, and I have two mixtures of Gaussians. So if you were to solve the optimal transport between them, you could recover, of course, this idea of Wasserstein distance between the two probability distributions. But more interestingly, what you recover is something called the McCann interpolation that was highlighted in 95 by Robert McCann, which basically tells you what is the shortest path between those two distributions in this Wasserstein metric. And from there, people started elaborating a bit more this story and comparing it, obviously, comparing this kind of interpolation with what would be the usual Euclidean interpolation. And in this case, it's very clear in 1D for univariate distributions that if you were to interpolate two densities, what you would get if you were to compute the mean density is something which is essentially those two things divided by 2. Whereas if you interpolate things in an optimal transport way, what you get is a lateral movement, if you want, between the two distributions. Let me just point out, by the way, that maybe this can help form even more intuition, that in this case, optimal transport is actually equivalent to looking at quantile functions. So instead of looking at distributions in terms of densities, which is one possible representation, you look at them in terms of quantile functions. So quantile being the inverse function of the CDF. So it's a two-step procedure to get from there to the quantile function. And what this does actually, what you recover as those densities here interpolating in optimal transport sense is actually the mixtures of quantile functions. So let me just show you a few more illustrations to help you form the intuition of why optimal transport is doing things differently. Here I have, again, 3 univariate distributions, and I'm mixing them in an optimal transport way. So I'm playing with them here. And here what you can see is that the interpolations are moving sideways, whereas here the interpolations are basically moving upside down. Okay? Of course, you can start playing with this. Why just limit yourself to 1D? And you can do this in 3D. And this involves a lot of computations that I won't have the time probably to present during this talk. But a lot of the progress that we made computationally has made this kind of interpolation possible. So here we are adopting a very, very naive perspective on shapes. Here we're just considering that one of those shapes here is just a probability distribution which is concentrated uniformly on its interior and 0 outside. And we just ask what happens when you just try to ask for interpolations in optimal transport sense. So this is one of the good cases. This is a success case. You can come up with other examples where this doesn't really work, but this seems to recover something that look at each between each interpolation as a more or less likely realistic shape. So we have a lot of those interpolations in the book and elsewhere, and they've been considered in other graphics conferences. So here again, I'm playing by interpolating between all those shapes by computing those barycenters. So let me just maybe write a parenthesis to say that this ability of the Wasserstein distance to be able to compare degenerate probability distributions, not necessarily distributions that have a density, but more generally measures, is behind the fact that it is emerging as a useful tool in high-dimensional machine learning. And one of the problems that people are addressing in that field is the notion of estimating generative models, also known as GANs. And in the GAN literature, what you're essentially trying to do is you are given observation in a very high-dimensional data space. Rather than trying to fit a density on this high-dimensional data space, which would be too challenging, what you try to do is try to come up with something that looks like data, distributed like data, but by playing a game, which is that you generate samples from a low-dimensional latent space and try to learn a mapping. Here I write it f theta, that brings your points in very low dimensions to high-dimensional space. And then what you're trying to do is minimize a discrepancy between those blue points and this red manifold. And the way people have done this in recent years is using the Wasserstein distance as well. So let me just, there are some applications to neuroscience, which are quite exciting, to NLP, to statistics. But let me just maybe close this very overview of some applications by saying that there's a very nice paper that was published 2 months ago in Cell, which basically uses optimal transport as a way to reconstruct the differentiation of cells across time. So the problem that they are faced with is, as a biologist, is you have snapshots of cells day after day, and those cells have some features. Here you can recover features using a messenger RNA features, and it's very high dimensional feature space, and you have them across time. And what you would like to understand is what is the likely evolution of one cell at one time and to another cell in another time. So you're trying to guess by looking at populations, individual dynamics. And this guess can be done using optimal transport. And so there's lots of applications like this that are pretty exciting and going on. And to give you the problem as it stands today is the following. For many years, in the computational world, we were mostly concerned with the idea that we wanted to compute the Wasserstein distance. I haven't talked about computation so far. I just told you that this was a nice tool, and it kind of made sense in applications. But I haven't told you how hard this is to compute. And it's quite hard to compute, and for many years, this was more or less the bottleneck. People understood that the Wasserstein distance was a nice tool, but applying it was painful. Right now, there has been a lot of progress in that field, and now what we're trying to do is, rather than just use this Wasserstein distance as a way to compare two things, more as a way to use it as a loss function, which is a bit what I tried to express earlier with this GAN problem. Rather than just saying this is far from this, I'm going to use the Wasserstein distance as a loss or fidelity term to say that this is what I would like to get. Let me just make this Wasserstein distance between me and my target smaller and smaller by computing basically the gradient of those Wasserstein losses. And if you look at the idea that you would like to compute a gradient in the space of probability distributions of this Wasserstein distance, then you fall on some very nice math literature from Ambrosio, Gigli, and Savare, and some very nice results in math as well, in PDEs by Otto in 98. So this concludes a bit what should have been my introduction, but I think I'm going to be a bit short on time. But let me take a bit of a turn now to explain why, in fact, many things that I told you, if I were to follow the official route, were a bit false. They're a bit wrong. And the reason why is the following. I've been telling you optimal transpose is beautiful theory from math. We apply it. I'm not telling you really how. We get nice results, and everything works well. But actually, if you really want to sell someone in data science the idea of optimal transport, there's two things that usually data scientists or statisticians or machine learning people look at. Is basically, okay, you want to propose a new loss function, or new loss, a new error term. How well does it behave in practice? And there's two things that usually concern people in statistics and machine learning is basically, well, usually those samples that I'm observing come from some underlying density. Okay? So whenever you give me points, there are just a sample from something that I would really like to target, which is what's going on if I had infinite access to samples. So one thing that you can ask is first, okay, since I will always use points, how bad is it to compute this Wasserstein distance between point clouds or measures? And the second question is, by doing so, am I doing anything that's meaningful in terms of what happens on the densities themselves? So it's two questions. Can you compute it? Does it make sense statistically? Or are you spending a lot of energy computing something that is completely different from what the statistics, from what the densities would give me if I had access to an infinite amount of data? So this trade-off between those two things, of course, is very important in machine learning. And what I can tell you is that actually, on both these two things, the original definition of the Wasserstein distance that I gave you scores miserably. It's terrible. It's terrible to use the Wasserstein distance as an LP for this on this aspect, and it's terrible to use it as well on this aspect. So let me just try to explain why. So imagine you're given a bunch of data, you have two probability distributions, and you want to compute the Wasserstein distance between them, the optimal transport. The way to do this, I'm going to gloss a bit of our notations, is just to write an LP, which essentially takes all of the elements of your two measures, their geometry, the distance between the points, and then the marginal weights to form this joint coupling, set of joint couplings. And then you solve an LP, which bad news or good news in this case, I don't know, is here it's at least cubic, supercubic in the number of points that you're considering. So if you do data sciences, you know that there's a very big threshold between cubic and quadratic, of course, and cubic is too much. And so that's a first problem. So this loss that you want to sell to someone doing data sciences needs cubic time to be evaluated. And the other bad thing is actually it's not a very well-defined object in the sense that if you use it on discrete data, this loss is not really differentiable in the sense that when you try to differentiate the minimum of an LP, you get into sensitivity analysis issues. And it's clear, easy to see that if you, for instance, change a little bit some parameters, let's say some x or y's, sometimes you will find an infinite amount of solutions. Okay, you will hit a facet, which doesn't really happen. But what really always happens is that you jump from one solution to another. Okay, so the big act of Kantorovich, which is to define optimal transport as a linear program, is beautiful when you compare densities. But when you actually compare point clouds or measures, you go into issues, which is that the output of that Wasserstein distance, the output of this linear program, is not differentiable. And so that's, of course, a big problem if you want to sell this as a loss. So two bad things. The first one is this is hard to compute, and it's not differentiable. What happens with the statistics? Well, it's also horrible in the sense that it's a very well-studied problem, and it's also related to the idea that quantization in high dimensions has to bear the curse of dimensionality. It's known that you can say that the expectation between this Wasserstein distance between two measures and what you would get by computing the Wasserstein distance between two samples is of the order roughly of 1 over n power 1 over d. So unless you are in dimension 1 or 2 or 3 sometimes, you very quickly hit the statistical barrier, which is that you will never get enough samples to approximate this using the actual computations of your LP. And this is well documented, and Quentin Berthet here has been working on this kind of problem. So two really horrible things. So contradict completely what I told you earlier. So what is really the story is, and is usually a bit overlooked, is that all of the papers that I showed you earlier usually start by saying optimal transport, Villani, Figali, beautiful mathematical theory. At some point, we're going to do a lot of hacks because it's dirty, but believe us, we need to do it, and it kind of works. And I think it's a bit head over heels, because actually, it's because you do those hacks when you play with optimal transport in data science that things work. And so it's important to also focus on the fact that we need to regularize things for these tools to work in data sciences. So there's many ways to regularize optimal transport. And we're considering in a lot of papers in applied literature. So for instance, if you look at the dual problem, you're taking the supremum over two test functions constrained by this cost. You might try to start adding some regularity on those two test functions. You might say, for instance, in the Wasserstein 1 case where you are taking the supremum over one Lipschitz function, that let's say, okay, Lipschitz functions is too big a set. Let's just consider deep networks with rectified linear unit activations that have bounded weights, and that will play the trick. Or you could use wavelet decompositions. In the primal problem, you can start playing with the cost. You're going to basically threshold the cost. There's lots of examples for this. In the measures, you might, for instance, say, okay, I'm going to approximate my measure by a Gaussian, and then optimal transport between Gaussians is easy to compute. I might project my measures on lower dimensional spaces, et cetera, et cetera. And one thing that I've been working on a lot is add regularity from this optimal coupling. And this is related, if you go to statistical physics, to the so-called Schrödinger problem. In applications, it's a bit more simple. It's related to an algorithm known as the synchron algorithm. So I'm not sure exactly how much time I have left because I started a bit late, but. Oh, 10 minutes. Okay. So maybe I might get to the 2/3 of the talk. So what I wanted to say is that if you look at any paper that uses optimal transport in practice, it will eventually use a lot of tricks or hacks. And I think it's a misnomer because those are probably actually important things to make things work statistically and computationally. So I'm going to present two such regularizations. So if I have time, I might talk a bit about this idea of entropic regularization, but because this is a bit older, and I assume maybe some people in the room might know it. I might overlook this, but there's lots of work on this. And I will talk a bit more about the recent work with my student, François-Pierre Paty, who presented this at ICML this year. So let me just start with, when is optimal transport very easy to compute and make sense? And this goes back to my introduction. Well, it's basically when you are on the real line. If you are on the real line and your cost between two numbers is just a convex function of the difference between those two real values, then optimal transport really boils down to simply computing the quantile functions of your measures. So let me just illustrate this. Imagine that you want to compute the optimal transport distance between this and this, not necessarily quadratic. It could be any function of the absolute value of the difference. So first what you would do is compute the CDF of the first distribution and the second distribution, then invert them. So take the symmetric with respect to this axis to compute the quantile functions. And then what you just do is you integrate between 0 and 1 the cost, or this cost function, over the difference between each of those things. Okay? And so here, when C is just the identity, well, it's very easy to see, this is Kolmogorov-Smirnov's test, that this thing is the same thing as this thing. Integrating on the inverses or integrating directly on the function is the same thing. Because it's the same thing to integrate horizontally here or vertically here. So that gives a very easy way to at least compute optimal transfer between two distributions on the real line. So what this motivated, this motivated the proposal, which is now used a lot, and it's arguably maybe the simplest alternative to compute the Wasserstein distances, which is to say, okay, give me any distributions that are high dimensionals in RD. I will sample directions on the sphere. I will project, so this is the push forward operator of the projection. I will project the measure mu and project the measure nu on this line. So what I recover is just two univariate distributions on this line. Then compute optimal transport between those two univariate distributions. And then keep on sampling and sampling and sampling directions. Of course, this has nothing to do with the real Wasserstein distance. When you could say that there are some, they are equivalent in the sense that you can sandwich the Wasserstein distance between below and above by this distance, but it's very different. It's a very different object, but still it kind of recovers some interesting properties. And if you're in high dimensions, and you know, I mean, you remember what I told you about this curse of dimensionality, it's useless to compute the Wasserstein distance anyway. So you might as well try to grab some inspiration for optimal transport and apply it in lower dimensions where we can hope something more meaningful is being captured.
So you're saying this is lower bounded by the standard base Wasserstein distance?
I think so, yes. No, you put, I think you can put the Wasserstein distance and lower bounded on the left and on the right by multiple of this. But I think there are some assumptions. I forgot it. To tell you the truth, I forgot about this. It's just now. Nicolas is behind you. Okay. I read it in the paper yesterday that I was reviewing, so it's not something that it might be wrong. So the other approach, which actually was the one taken by Philippe Rigolet, in this paper by Cell that I told you in biology, is I told you earlier, maybe I can go back to this illustration. In this application, what biologists are tracking are probability measures of cells in dimension 5,000, and they try to, by simply computing optimal transport between two time steps, to recover what could be a good notion of descendant of or ancestors of a cell. the computational problem they run into is that they're actually using representations for each cell. Those are measures in dimension 5,000. Okay? And if they find, of course, and everybody would, that computing optimal transport in that case, in dimensions 5,000, is meaningless. So what they do is the following. They do PCA first, which is what would be maybe the simplest approach. They first do PCA of the entire point cloud, and then project on K subspace of that PCA, and then compute the Wasserstein distance between those two things. So it's a two-step approach. The problem is that you can imagine a lot of scenarios where this would go wrong. One, for instance, is this. You have a measure like this, a measure like this. If you pull those two samples, the first axis of PCA is this, of course. But if you actually project this on the PCA, the Wasserstein distance between these two things is 0, right? So although this is a common practice, or recently, but I think it's a meaningful practice to do first PCA to reduce dimensions, to do something that is meaningful in terms of optimal transport, there is something a bit inherently wrong in doing this in a two-step approach. So what we proposed is, instead of doing this as a PCA first and then optimal transport, why not directly look for a robust version of optimal transport whose aim would be to find, just as in PCA you try to find the subspace where there is more signal, here we would try to find the subspace on which you project your two measures for which the Wasserstein distance is maximized. Okay? So it's a fairly intuitive process where you imagine your point in high dimension, you project it on a subspace, here dimension 2, and then you try to look for optimal transport, and you want that the optimal transport in this subspace is maximum. So there's nice things statistically to be said about this procedure. I'm not sure if Jonathan Weed has published those results, but he has shown that if indeed the measures are supported themselves on a subspace in this high dimensional space, this procedure would somewhat recover a much better statistical sample complexity. The problem is that this thing is not a convex problem, because the set of all those projection matrices is not. So what you can do instead is look at the mean max. So instead of having max of the Wasserstein, which is a max mean, just look at the minimum over all joint couplings of the maximum over all projection matrices of those costs with respect to P. And here something interesting happens, which is that when you use this Wasserstein 2 in the square Euclidean distance, of course, there's a very nice, very usual way to rewrite this. So this is the distance between x and y once they have been projected. And it's the same thing as taking the dot product in Frobenius for matrices between E transpose and x minus y transpose. So when you look at this expression, it seems to be mixing, of course, E and P with a quadratic here, but actually it's just simply the dot product of a matrix of size d times d, which you can interpret as a matrix of second order moments of transport with the dot product of E transpose. And so let me just try to illustrate this. Imagine you have points x1, x2, x3, x4, y1, y2, y3, y4. You come up with a transport, something that basically maps one point to another. So what you can see is that if you look at all of those displacements, so this is x minus y, which is basically weighted by your transport, you have a set of vectors. And what you are interested is basically looking at a second order moment of those vectors. Now, if you have another transport, this is another valid transport, it will score differently, right? It will have different directions that it's weighted on. Now, the interesting thing is that this, of course, this max over all subspaces is just simply an eigenvalue problem. If you just take the maximum over all those E transpose, etc., you just get that you recover the sum of the first top eigenvalues, the k top eigenvalues of this matrix VP. So to summarize, this notion of subspace robust optimal transport is essentially looking at what are the transports, the couplings, whose matrix VP has the smallest top k eigenvalues. And if k is equal to d, then you recover simply the trace of this, and the trace of this is just simply the transport cost, the regular one. So here, for instance, it's an interesting example. It seems that the green, for instance, transport is cheaper. right? If you look at the length squared of all those vectors, it's clear that this is smaller than this. But if you look at the top eigenvalue, the first eigenvalue, for instance, of those two vector fields, the second order moment of those vector fields, then this one is better. So what you're doing by taking the subspace robust thing is you're constraining, you're looking for something different, which is not just simply the total amount of displacements squared, but more what is the regularity of those displacements. So I think I need to cut this. So this closes my talk. Thank you very much. Maybe I can conclude with one slide. So to conclude, optimal transport is really a gold mine, I think, for people in statistics and data sciences. It has a lot of very interesting ideas. On the other hand, I think it's doomed to fail if we directly apply the definitions that were provided by mathematicians. So this interplay, I think, is very exciting. Usually what I observe is that a lot of computational advances happen first, and then people try to study them statistically after. And there's a lot of exciting literature also in statistics that's appearing. And also the applications are slowly appearing as well. I'm particularly very happy about this work in biology that seems to be meaningful. Thank you very much.
So I think we have time for one short question.
Is your slice, or the new one that you did?
Yes.
Is it still a path space? Or
So it's a geodesic.
do you have
space.
geodesics?
Yes, we have geodesics. Yes, we do have. We haven't used it, but we have proved it. Yes?
Just a quick question. So I thank you very much to this point of regularization. I mean, once you start to regularize, I mean, is there any information theoretic argument you can give for actually using the Wasserstein distance or something like that instead of, say, KL? I mean, so for KL divergence, usually there's some information theoretic justifications that they do well on prediction error and so on.
Yes.
With Wasserstein, it just seems to be around because of Villani and Figali, and it's kind of cool now. But is there any sort of deeper reason that you could give to be slightly provocative?
No, you have a point. I think one of the examples that is interesting is when you, for instance, is this GAN literature. The generative models thing is interesting. You're basically trying to fit a very high dimensional distribution with a low dimensional manifold, and then there's no real alternative on using KL or things like that, I think. So it's basically a more robust, I think, notion of similarity, discrepancy between distributions. The other thing is I really see them as kind of orthogonal in the sense that in optimal transport, we really rely a lot on the base geometry of the space. And somewhat we can handle strange measures which are very degenerate. In KL, we never use the geometry to define KL, but somewhat we put it a lot in the densities that we use, Gaussians and things like that, which are already containing a lot of the geometry. So to me, it's like two different routes. One, in Wasserstein, you're putting geometry at the base, at the level of the discrepancy, and then you're playing with strange or like discrete distributions, for instance. So I don't think I have a definitive argument in stats so far. Like this minimum Kantorovich estimation, so minimizing the Wasserstein distance between a data and a model. In GANs, it seems to be working, but it's very difficult to draw anything out of it. And then in terms of information geometry, I know that people like Amari have been working on trying to understand some notion of information geometry of the Wasserstein distance or regularized versions thereof. So still a bit the far west.
Okay, so let's once more thank for both of the speakers.